Hi, I'm Jinyang Shao. I'm an undergraduate student from Wuhan University, China. Today, I'm going to talk about testing object detection. Autonomous driving systems are widely developed in automobile manufacturers. In an autonomous driving system, object detection is a key module that is used to identify objects from images, such as persons or vehicles on the road. It is necessary to test the object detection models ahead of autonomous decisions to evaluate its reliability. Most of effective object detection tools are developed based on deep neural networks, but the input and output of deep neural networks are not directly correlated. This makes testing DNN or DNN-based object detection difficult. Our motivation is that we want to propose a technique that can efficiently test the object detection system and provide a guidance for the system to improve the detection accuracy. Existing work conduct image synthesis via metamorphic testing to examine failures of object detection. Metamorphic testing successfully solved the test oracle problem by comparing two execution results of the program, but their synthesis method is randomly insert an object into a background. In autonomous driving system, the input photo of object detection is taken from onboard cameras. That is, if a synthetic image is different from naturally looking image, the image may be not used to test the object detection in autonomous driving system. Therefore, we propose a uniqueness strategy to generate natural-looking synthesis images, which can be used to test the object detection system. We define the equality criteria for metamorphic testing. Simply speaking, the detected object in the original image should be detected in the new synthetic image. We use mean average precision to check the metamorphic relation. The workflow of our tools is started from the origin autopilot image dataset. We divided the image into two sets after background information estimation and object selection. We use 3D reconstruction method to generate synthesis image. Here is the example of the implementation of our tool. First, we extract objects from images. As for background, we use the line segment detection and the depth estimation to help us guess where is the vanishing point located. Then we use the 3D message to determine the location and the size of the object to be inserted. In our experiment, we used 200 images from the origin Apollo dataset to generate 755 synthesis images. We use both vanishing point-based insertion and side insertion as comparison. Then we use the synthesis image to test the YOLO version 5 small model. After comparing the detection result in origin image and the synthesis images, we can evaluate the detection accuracy. We define three kinds of detection failure. Recognition failure is that objects that could be recognized in origin image can no longer be recognized in the synthesis image. Classification failure is the category name prediction doesn't match the ground truth. Location failure is the bounding box doesn't match any of the ground truth box. As the table 1 shows, nearly 70% synthesis image cause detection failure. Table 2 shows the number of different types of failures detection in the synthetic images. Recognition failure and location failure is in the majority. In conclusion, we successfully generate large amount of natural-looking synthesis images that can be used for testing, finding detection failure, and data augmentation. Thanks for your listening.